Hello everyone. My name is Sulaiman Al-Mamari, and I'll be the presenter today. My colleague Humoud Al-Ghanem will be the discussion leader. Our topic is data transformation, an essential pre-processing step in data mining that prepares raw data for accurate and meaningful analysis. So, what is data transformation? Data transformation is basically about taking messy, raw data and shaping it into something useful. Think of it as organizing a storage room before you start working. Everything needs to be in the right place and format. We do this to fix a few key issues. Some columns might be completely different scales, like age measured in years and income in thousands. Some numbers could be heavily skewed, making patterns harder to see. And sometimes, data just doesn't match. Maybe dates are written differently, or units aren't consistent. Once these problems are fixed, the results are powerful. That becomes cleaner, more consistent, and easier to visualize. And the models we build afterward, whether for prediction or pattern discovery, perform much better because they're learning from well-structured information. Now that we know what data transformation is, let's look at why it's so important in real-world data mining. In most datasets, not every feature speaks the same language. Take a simple example: age ranges between 20 and 70, but income can range from 1,000 to 1 million. If we feed this data into a model, the algorithm will focus more on income simply because the numbers are bigger, even though age might be just as important in predicting a pattern. For instance, in credit scoring or customer segmentation. That's where transformation steps in. By scaling and adjusting these features, we make sure every variable contributes fairly to the outcome. It improves model accuracy, so predictions aren't biased toward high-valued attributes. It also boosts algorithm performance, especially for optimization-based models like gradient descent. They converge faster and work more efficiently when the data is balanced. And finally, it enhances interpretability, making it easier for us to understand which features truly drive the results. So in short, data transformation plays an important role in turning a chaotic dataset into one that's fair, balanced, and ready for mining. So now that we've covered scaling and numeric transformations, let's talk about another challenge: categorical data. Most data mining or machine learning algorithms can't work directly with text or labels. They need everything in numeric form. That's where encoding comes in. It's how we translate words into numbers without losing meaning. There are a few common techniques. First, label encoding. It's simple: each category gets a number. For example, if we have colors like red, green, and blue, we might assign them as red equals 1, green equals 2, and blue equals 3. It's quick, not ideal when there's no real order between categories. Next, we have one-hot encoding. This method creates separate columns for each category, so if the color is red, it becomes 1 in the red column and 0 in the others. It's perfect for nominal data, things without natural order. And it prevents the model from assuming that blue is somehow greater than green. Then there's ordinal encoding, which is great when categories actually have an order, like low, medium, and high. It assigns them as 1, 2, and 3 to preserve that ranking. Finally, target encoding replaces each category with the average of the target variable. It's often used when there are many unique categories, but it has to be done carefully to avoid overfitting. Choosing the right encoding method is key. It helps the model understand the meaning behind the data, without creating false relationships or bias. Now that we've seen how to handle categories, let's move to continuous data, numbers that can take endless values, like age or income. Discretization, or binning, means converting those continuous values into groups or ranges. For example, instead of individual ages like 22, 35, 48, we can group them into 20 to 30, 30 to 40, and 40 to 50. This makes data simpler and reduces the effect of outliers. It also helps capture nonlinear patterns, which is why algorithms like decision trees or naive Bayes often perform better with bin data. In short, binning helps noisy, detailed numbers into clearer, structured insights. Now that we've prepared our data with scaling, encoding, and binning, sometimes there's still one more issue: the shape of the data itself. In many cases, values are not nicely distributed. They can be skewed, meaning most values sit on one side while a few extreme ones stretch the scale. That's where mathematical transformations come in. They help us reshape the data to make it more balanced and stable. This is especially important when models assume normality or equal variance. For example, imagine we have income data. Most people earn between $1,000 and $3,000, but a few make over $100,000. Those values create a long right tail. If we apply a log transformation, those large incomes get compressed, and the data becomes more symmetrical, easier for algorithms to interpret. A square root transformation is similar, but works best for moderate skewness, such as number of products sold per day. Meanwhile, the reciprocal transformation, which flips values like 1/x, can drastically reduce the weight of large numbers, helpful when a few extreme values dominate the dataset. Finally, power transformations like squaring or cubing are useful. When the data is left skewed, meaning it has a long tail on the smaller end. By amplifying the higher values, we bring balance back to the distribution. In short, these transformations don't change the meaning of the data. They simply make it easier to visualize, compare, and model. It's like adjusting the lighting in a photo. The details were always there, but now you can actually see them clearly. In conclusion, data transformation isn't just about cleaning data. It's a performance driver that directly affects how well our data mining models work. When data is properly transformed, everything becomes easier. The patterns are clearer, algorithms learn faster, and the results become much more accurate and full. We can think of it as a small pyramid of benefits. At the base, transformation helps with faster convergence. Models train more efficiently because the data is consistent. Then comes higher accuracy, as features now contribute fairly. On top of that, interpretability increases, making it easier for us to understand why a model behaves the way it does. And at the very top, we achieve better insights, turning raw numbers into valuable, data-driven decisions. The core principle is simple: well-transformed data equals better models and smarter insights. Thank you for listening. Now, I'll hand the mic over to my colleague Humoud, who will continue as our discussion leader.